So this actually slots, I think, quite nicely between the last talk and the next one. I will talk about, as Tom just said, informatics resources, and the emphasis here really is on sort of large-scale tools rather than algorithms or applications. So I take the goal of meta-analysis, or at least let's say one goal, it's a fairly important goal, to be basically trying to make sense of the fMRI literature. I mean, I think that's one of the nice things of a meta-analysis is you have, in theory at least, the prospect of taking a diverse set of studies that maybe give you different results and somehow combining them into some sensible consensus estimate of something you're interested in. But if you just look at what actual fMRI data looks like, at least coordinates, it very often looks like this. So this is from a paper from Hedy Kober and Torweger 10 years ago now. And there's a meta-analysis of emotion studies, 437 emotion contrasts, I think something like 150 distinct studies. And if you were just looking at this, or if you just threw this up and looked at the raw data, you might be tempted to say it's basically uniform, right? It doesn't look like obvious that there's structure there. But as you've already heard, there are actually lots of ways that you might go about trying to quantitatively synthesize this in order to try and make some more reasonable claim about what's going on besides just, well, the whole brain is lit up by emotion. So you've heard about ALE and also MKDA to some degree. I'm just going to show you a little bit of MKDA, but functionally it doesn't really matter for my purposes what you're using here. The point is you start with individual maps, right? So here's one study, here's another, here's a third, and they vary pretty dramatically in how much stuff they might report or what the designs are, et cetera. And in the case of MKDA, you're really just multiplying, you're just convolving each of these points with a hard sphere. So you have this essentially a smooth image, and then you can just average them to take some weighted average. And like Tom said, the interpretation here might be something like, well, 12% of studies in this data set activate the amygdala here, and maybe other regions not so much. And then you can do some permutation-based statistics. Here's your null distribution, and the regions or the voxels that show a higher density of effects than you would expect by chance you will call significant, and you end up with this, right? And so using these kinds of methods, you go from something like this, which is very hard to understand and easy to fool yourself into thinking you see some patterns that might be interesting, to this, which is much more orderly and sensible. And so now you can see, well, this is sort of, at least as of 2008, things may have changed, although I suspect for this granularity of analysis, probably you'd get the same thing now. You could say this is sort of the emotional brain in some sense, right? If you ignore construct validity and say, like, just let's treat these 400 contrasts as if they were a perfect representation of emotion, there's your emotional brain, which is very different from the top panel. And you can go and meta-analyze all the things, and you've already heard lots about the different kinds of approaches you can take and the different domains you can apply them to. Here's just a few examples, right? You can apply these tools to task switching, subsequent memory, smoking cure reactivity. It goes on and on. If you can find, I was going to say a few studies, but after Simon's talk, which I agree with, so let's say 20 or 30 studies, then you can do something like this and produce an estimate of consensus neural correlates of the thing you're interested in. And that's great. And the question I want to take up is, can we scale this up? So there's no question that you can do this for essentially anything, any domain, any process that you can identify a reasonable set of studies for. But as Simon made clear, and as Felix pointed out, right, this is very time-consuming. If you want to do a good job, you should generally want to do a good job, but you can only do so many good jobs, right, before you run out of time. And so if we want to have some way of maybe scaling this up and doing a less good job on a larger scale, that I think is also important. And so the question here is, sure, we can meta-analyze anything, and there's no doubt that the results often provide a clearer window into the neural correlates of the thing we care about. But given that there's this meta-analysis is really time-consuming, the question becomes, is there a way to speed up the process? And you've already seen one way, which is to use existing large databases like BrainMap, right? So if you can grab a bunch of studies that someone else has already gone to the trouble of coding and submitting them to analysis, that's great. That saves you a lot of time. But even this has scaling issues because it doesn't grow very fast. It's still the case that for a database to get into BrainMap, somebody has to sit down and carefully annotate it, right? And so there's a fundamental ceiling on how fast that can grow. The question I'm interested in is, can we develop neuroinformatics resources that allow us to conduct meta-analyses at scale? And again, I kind of will affirm something Simon said, which is there's a quality-quantity trade-off. And both of these, I think, are important. So you can spend a lot of time very carefully doing a meta-analysis of 15 studies that nobody else has ever coded, You can use databases that are out there and pull data from a larger number of studies that have already been extracted. But it'd also be nice if there's just sort of an exploratory tool you could appeal to and say, look, there's 800 studies, and we just want a very simple average almost of these studies to get a sense of what might be going on. And so a few years back, some colleagues and I introduced this platform, which many of you are probably familiar with, Neurosynth, which lives at neurosynth.org. And Neurosynth really is several things, primarily a website, but it really, but just below that is a database, and it's a database of currently 11,000 studies. It hasn't grown in about 3 years now, but I'm happy to say that hopefully within the next month or so it will be substantially expanding. But that's still a lot of studies. That's probably about 20% of the literature as a whole. It is also a set of Python tools that you can use. So if you're more comfortable doing stuff programmatically, then all the stuff that is on that website can be generated fairly easily with a set of Python tools. And most importantly, it is a Twitter account. It's a kind of a cheeky Twitter account. So this is Neurosynth a couple of weeks ago, insisting that it was going to be updated very, very soon, and everyone should be very excited. But then Neurosynth realized it got a bit ahead of itself and scaled back that prediction. So hopefully some point in the next, let's say, couple of weeks, there will be a big update. Okay, how does it work? I'll give you just a very simple, very high-level overview. And after I give you that overview, we'll say, really, that's all there is to it? And the answer is yes, that's all there is to it. It follows a philosophy of if it looks like a duck and quacks, then it is a duck. So the idea is really, for Neurosynth purposes, anything that looks like brain activity will be considered as such. What does that mean? That means that we have a parser, and the parser takes HTML articles, and it pulls tables out of those articles, and then it just looks for things that look like XYZ values. If it looks like an XYZ coordinate, then it is one, right? No questions asked. So thankfully, we know that many people report their data in tables that look like this. Right here's the coordinate information. The brain is this nice three-dimensional object. We have these orthogonal planes, so we can identify within that general framework where activation is occurring, where peak activation is occurring, and that's essentially it. So the idea is that if it's reported in this table, we say that's an activation. Notice what this does not include, right? It does not include everything Simon talked about, everything Felix talked about, right? Is it positive activation or negative activation? Is this coming from the schizophrenic group or the controls? You might think all these things should matter a lot, right? You might think this should make it completely impossible to do meta-analysis. That was certainly my intuition. Turns out maybe it's not, critical, at least for some things. And the other side of things is the semantic one. So we can do this sort of very simple, almost mindless pulling out of coordinates on the brain activity side, and we're doing essentially the same thing on the semantic side. So we take abstracts of articles, and we do what computational linguists call a bag of words approach, which is we just treat the abstract like an unordered set of words. And so if a term occurs with some minimum frequency, which happens to be once, in an abstract, then the study is about that thing. So if the phrase, "we show that painful stimulation elicits colorful language use," occurs in the abstract, congratulations, you now have a study that is about pain and language and colorful, right? All those things. Clearly, this is not a sane assumption. If you really wanted to make strong claims about the world, this is not how you should be drawing conclusions. Nonetheless, if you're willing to make that conclusion, or make that assumption, then you can set things up quite nicely where, in effect, what you're doing is you're saying, hey, let's do a term-based search in the literature, pull out all the studies we know about that use the term pain, and you get some studies. And then we have this parser that just extracts coordinates automatically with lots of error again, right? But it does. And at that point, you have just a giant spreadsheet. So just like everything you've seen to this point, you have this spreadsheet that contains activation data about lots of studies. And the only difference between this approach and what you saw is that the data quality here is horrendous in comparison. But there's potentially a lot more of it because all you had to do was do like a quick search. And at that point, of course, you can submit this to any kind of meta-analysis you want. So any of the algorithms you heard about today, or potentially others, you can take this data, feed them in. And the question really then just is how good is the data, right? Because we know that the extraction procedure is not very good. What kind of results come out of this? So setting aside from the question of quality, what can we do with this? Well, if you allow yourself to think this could work, then it gives you a very powerful framework, right? Because you can go from sort of semantic tags on the one hand to this enormous database of brain activity on the other, and you can generate all kinds of mappings between those things, and you can generate those mappings on a fairly large scale. So I'll give you just a couple of examples. One thing you can do, even though you should never do it, but you can, but you shouldn't, is you can do reverse inference with a star, which is like reverse inference, but much worse. You can, in theory at least, estimate the probability that some term is used conditional on activation. Now, this is not in any way unique to Neurosynth, right? Given any database like BrainMap or anything else, you can estimate the probability of some label or some tag conditional on some pattern of brain activity or vice versa. So in some sense, you can compute whatever conditional probability you want between going backwards and forwards. So what we're asking here is essentially, how likely is a study to use the term? Remember, these are terms, right? They are terms that occur in abstracts. They're not processes, cognitive states. Arguably, the same is true for tasks, just as an aside, right? A task label is not the same thing as a process, and it's really important to remember that because almost nobody's actually studying processes in fMRI. We are studying labels that we kind of pulled out of the air, essentially, for our tasks. Nonetheless, we can ask that question, and then we can conduct meta-analyses quantifying that association between a term like language and some pattern of brain activity. So we can ask, is term T statistically associated with voxel V? So we can get an index of association. And you have these, so Neurosynth website has these maps, although for reasons that are very difficult to explain and amount to me being very lazy, the reverse inference maps up there are actually this thing and not this thing. So that's a good thing to keep in mind, and hence the star. The important point is this can be fully automated and done for thousands of terms. So it's very easy to punch a button and get out lots and lots of maps at once. And so here are a few of them. Right? So here you have a meta-analysis for action, arousal, attention, auditory, conflict. And I think if you scan these, if you work in any of these domains, you can look at these and they will generally look reasonable. There are some exceptions, which we could talk about, but by and large, I mean, I think what you see is what you would get if you do a careful meta-analysis on a domain, a broad domain. So for things like reward, you can see here's a published paper. I had nothing to do with this paper. There are a few others like it that show that if you just take the Neurosynth analysis for reward and you compare that to positive reinforcement, you get a very similar pattern, and the same thing for negative reinforcement. This is based on, I want to say, like a few dozen studies. This is maybe 500 or 600 studies. And that, I think, is why it works, because for the term like reward, there's just so much data that averaging over all of these terms does the same work that something like this does. But this would not work if you were doing something like thermal pain versus mechanical pain. If you want to understand the difference in neural correlates, Neurosynth is not going to help you because we don't have 600 studies for each of those terms. So I'm a big believer in the power of aggregation, but there's lots of cases where aggregation is just not possible. Right? There's lots of other things you can do on the website. So just in interest of time, I won't get into detail. But you can visualize functional connectivity maps. These are actually not from Neurosynth. They're provided by Thomas Yeo and Randy Buckner. Functional connectivity from 1,000 subjects. You can overlay Neurosynth coactivation. You can plug in a particular coordinate and ask, well, what are the sort of strongest associations? And this is, I think, very useful just for exploring. I would probably stick to exploring. Like, I don't think anybody should be taking these numbers, sticking them in their papers as a finding. But it's a good way to orient yourself to what is going on in the brain region, broadly speaking. What are the associations? For those of you who are more comfortable with code, we provide programmatic access. So almost everything on the website can be accessed via an API, which is there, and there's documentation. And so please don't scrape the website for 200,000 images. We can make that much easier for you. There are Python tools for more sophisticated applications. Importantly, all of the data are public. So everything is in the public domain. You don't need to email me for permission. Do whatever you want with anything. In fact, please don't, maybe drop me an email and tell me what you're doing because I like to hear, but don't write me a long email saying, hey, could I please do this? And yes, the answer is yes. And there will be more coming soon, hopefully, pending grant funding. Definitely the database will be expanding through 2018, so there'll be about 3,000 more studies in the next couple of weeks. Let me skip over this. Interpret carefully, I will say. Now, obviously, there are some limitations to this. I've mentioned the data quality limitations, but there are some limitations that are just inherent to coordinate-based meta-analysis, and you've heard a little bit about those already. Fundamentally, coordinate-based analysis is, let's say, suboptimal. And the reason is very simple. Here is, and Tom kind of already made this point, right? Here is what actually comes out of your study. Let's pretend this is like a gigantic sample, good methods, et cetera. You have continuous data here. And this is what's actually reported in the paper. This is like extremely thin abstraction. And we are trying to reconstruct this from this, and it's just a very difficult thing to do. So we would be much better off if we could actually use these kind of things. Just to kind of make the point, here's a study from Tom's group a few years ago. This is a gold standard. I want to say this is what, like eight studies or 10. Yeah. And so that's the gold standard. This is image-based meta-analysis, although this is fixed effect, so it's a little overpowered, actually. But you can see that you get, this looks much more blobby and coarse-grained, right? And you get some signal, obviously. You reconstruct some of it, but not all of it. So what's the solution to that? The solution is, and Simon alluded to this as well, to share maps. And for a long time, that was sort of a tough sell, because where would you put the maps and how would you organize them? And thanks to the effort of Chris Gorgolewski and Russ Poldrack and various other people, we now have a platform called Neurovault, which is very easy to use. It's a whole brain repository of maps. Russ will tell you a lot more about what you can do with it. I will just point out that if you go to Neurovault and hit Get Started and upload an image, in about 5 minutes you can upload a bunch of your maps and have them represented like this on the website. So here are all your different maps. You can see there's Z-maps. You can interactively navigate this. It even implements Alex Huth's PyCortex viewer, so you can have a nice 3D visualization, and you can collapse it and unfold it. You can do that for a good half hour. It's very entertaining. And here's an example of an individual map. So purely for visualization purposes and storage, you have this very easy-to-use resource where you can point people to in your papers. Right? So instead of saying, contact me if you want this map, you just drop a URL, and that will be there hopefully forever. Now, I mentioned that there are other things you get out of this. It's not just being altruistic and sharing. For every map, there is this very important analysis button. And we let you do cool stuff with that. So you can actually interpret that image in various ways. You can find other images that are like it. And Russ will talk a lot more about that, so I'll stop there. I could talk a very long time about other kinds of informatics resources. I'll just sort of allude to things that are coming down the pipeline. They don't exist yet, so I didn't, some of them at least. But I do think it's an exciting time because we are seeing things like, so some of us are in the process now of developing a common framework for meta-analysis in Python, which is not, well, it's on GitHub, but I wouldn't recommend using it just yet. You might be noticing a theme here. Better Neurovault integration is in the works with other resources. So there are already plugins for SBM, for example, that let you push your SBM results straight to Neurovault. The same will be true eventually for OpenNeuro and for other platforms, so that you can basically very quickly push your results to Neurovault instead of having to take, doesn't take much time, but even that extra 5-10 minutes can be a barrier. And if all goes well, then at some point, I've been saying this for a long time, you probably shouldn't believe me, but at some point in the future, there will be an online meta-analysis suite. So everything that Neurosynth does right now that's static, in theory, and I think in practice, should be done online, in the cloud, right? The mythical cloud. So that you can come along and you can grab studies and you can annotate them and you can code them however you want, and all of that without actually downloading, installing anything, and just in real time generating results, pushing them back to Neurovault, and so on. So let me just very quickly conclude. I do think this is an excellent time to be doing meta-analysis. Right? So I think, I don't think many people would dispute that a lot of the sort of strongest conclusions we've been able to draw in the literature have come directly out of meta-analyses. What's nice is that we're now seeing an explosion of tools and large databases that make it much easier to do meta-analyses. There are common standards and frameworks under development, so I think it will continue to get easier to do interesting things. And I will put this plug in. I mean, I agree on the one hand with Simon that very little of the literature right now is available in image form, but I think that's actually going to change rapidly. In fact, Neurovault has been growing exponentially for the last 2 years or so. So I think a non-trivial fraction of the literature actually already is in Neurovault, and I think within a year or two it'll be to the point where we can actually start doing some really interesting things. So I'll stop there. Thank you.